So the first question is going to be an electrochemical cell is constructed using the two-half cell. Okay, so you can see from this question here, they mentioned that okay, this one is going to be Br2 and Br minus. So it's a gas and ion. Okay, gas and ion. So if you have gas and ion, okay, the electrode that we use is always platinum. Okay, and then you have aqueous and aqueous. Okay, or ion and ion. So the electrode that you must use is going to be platinum. So state the material used. Okay, just state. So platinum. Okay, and then platinum. Okay, be very careful. Unless we are talking about metal and metal ion, then you use that same metal. Okay, so this one is going to be important. Now the cell is operated at 298, and they are asking, they are telling the Br2 and Br minus half cell has standard condition. So standard condition is 1 mole per dm cube. So no issue with that. Okay, but the problem is going to be the Mn3 plus and Mn2 plus. Okay, it's going to be a different concentration. They are non-standard condition. Okay, so what we need to do is, okay, we need to use the Nernst equation, okay, to calculate the E. So this is going to be non-standard condition. So whenever you have non-standard condition, the formula is going to be E. Okay, hold on, yeah. Okay, the formula. Okay. Okay, let me open it again. Okay, the formula of Nernst equation is going to be the E. Okay, E is going to be E standard. Okay, E standard plus 0.059. You please remember this. Okay, 0.059 divided by Z over there. This is Z is going to be the charge or the number of moles of electrons that you use. Okay, and then you times with. Okay, normally they put in your book and in my I think in my PowerPoint slide also, I put log oxidized form. Okay, log oxidized form. But please remember, okay, we didn't put the reduced form, okay, because the oxidized form and reduced form, because in that example in the textbook, okay, they put it as a metal. Okay, so do remember, if you are talking about metal, okay, copper 2 plus 2 electron to give you copper, for example. Okay, so if I put the here follow the oil rig, okay, oxidation is loss of electron, reduction is gain of electron. So you see this one, Cu2 plus is being reduced. Okay, it's been reduced. So this Cu is the reduced form. Okay, reduced form. Now, reduced form, when your reduced form is going to be in form of metal, you don't calculate the concentration of metal. Okay, that's why the reduced form is constant. Okay, that's why in your textbook they say log oxidized form only. Okay, but you must remember the actual formula is not that. The actual formula is oxidized form divided by reduced form. Okay, so here is very important because there's oxidized form and reduced form. Okay, so here when you look over here, when I put the Mn3 plus, okay, when they add electron to give you Mn2 plus, I need to identify which one is reduced form, which one is going to be oxidized form. So when I see it here, I know something is gaining electron. So this is being reduced. Okay, Mn3 plus is being reduced. So Mn2 plus is going to be the reduced form. Okay, so Mn2 plus is a reduced form. So this is reduced form. So that's the first thing that you need to find out, yeah, which one is the reduced form. So when I use the formula, okay, 1.49, I get it from your data booklet under the standard condition. Okay, 1.49 plus 0.059 divided by what? Okay, so here, okay, the Z is going to be 1. Okay, but if you have copper, the Z will become 2. Okay, please be very careful on this. Okay, so it's supposed to be 0.059 divided by Z. Okay, so that's the formula. Okay, but in this case, divide by 1. So log what? Okay, log oxidized divided by reduced. Okay, I do not know how you're going to remember. Maybe you remember by OR. I don't know. Okay, please remember this. Okay, so oxidized divided by reduced form. The reduced form, okay, I know that it's going to be 0.1. So 0.1 is the reduced form. This is oxidized form 0.5. Then I use the formula and I calculate, I will get 1.53. Okay, so when you give your answer, please include plus. Okay, plus 1.53. Okay, now we want to calculate the E cell under these conditions now. Now, we will not use 1.49 anymore, okay, because this is a non-standard condition. So we will use whatever that we calculated over here, 1.53. So I put, okay, the equation 1.53 over here, okay. Once I have that, okay, I will look at the periodic, my data booklet, what is going to be the E value for BR2, okay. So BR2 to become BR minus. So when I compare, okay, I want to compare, I need to find out which one is more positive. Okay, then I put them to the right. It's moving to the right or something like that. So here I can see that 1.53 is going to be more positive than 1.07. So this will be moving to the right. Okay, so if this is moving to the right, yeah, maintain 1.53 is positive. But I know this one will move to the left. If it is moving to the left, then it's supposed to be negative 1.07. Okay, so when I add this, okay, what I'm going to get, I am going to get positive 0.46. Okay, and this is going to be the extension to that. Okay, what actually happens, this is going to move to the right. Okay, move to the right, and this one moving to the left. So BR minus to become BR2, BR minus to become BR2. Okay, but you need to balance the electron, because the 2 electron here, you need to times by 2. Okay, do not ever times 2 over here for EM. Okay, please remember that. Okay, so you times 2 because you want to eliminate the electron and electron will cancel. Okay, here you are going to get this equation. Now, please be careful. You can double check the marking key. Okay, your marking key is not always correct, right? Even though it's coming from CIE. Okay, your marking key has error. Please check. Okay, in your marking key, they ignore the 2. They put 1. Okay, that is wrong. Okay, you must have 2 there. Okay, so please double check. Okay, double check. Don't follow blindly. Okay, what the marking key has written. Okay, double check. If you're not sure, okay, just ask me. Yeah, I will try to help you out. Okay, but okay, I have written over here. You know the aqueous condition, aqueous, and then this is gas. So I write down. Okay, now, okay, please check. Marking key has error. Next, okay, this one, the other day, Jody has asked me also. Okay, it's good. He asked me also, so it's okay. I'll show you again. An aqueous solution of copper 2 sulfate is electrolyzed, okay, using copper electrodes. A current, okay, is passed for 3 hours, and then you are going to have certain mass deposited at on the cathode. Okay, the charge is given. Okay, the relative atomic mass is given. So we want to find the Avogadro constant. Now, you cannot use the normal way, okay, of us calculating, okay, like copper 2 plus 2 electron to give me copper. I cannot use the normal way for this, like saying that, oh, 2 Faraday is going to give you 1 mole. Okay, I do this calculation, then I try. Then how are you going to calculate the Avogadro constant? Okay, so you cannot use the you should not even use the Faraday. You should not even use 96500 column over here. Shouldn't. Okay, you shouldn't. Okay, so this is going to be, we are going to use like I think we did an activity about investigating Avogadro constant. Okay, so that investigation when I did, okay, was done, okay, even before this question actually came out in this paper. Okay, so I was using it in 2018. Okay, so you see a 5 marks question came, okay, based on the worksheet that I've created before that. Okay, so it means it's possible that they try to ask every single type of question, investigating and so on. They don't like to ask the same thing over and over again. So this is a very interesting question. So how do we do that? Okay, Q equals to IT. Okay, so you just put the I is 1.5. Okay, 3 hours, you change it into seconds. Okay, times 60 and 60. So you have this. So what do we have over here is I know, okay, when you have in this, okay, equation, if you have, okay, 2 moles of electron, okay, 2 moles of electron, and you see 2 moles of electron, and this it depends on the Avogadro constant, because we know every one Avogadro constant is going to represent for 1 mole. Okay, so I'm just going to use the L as my Avogadro constant. It means that 2 times Avogadro constant, okay, and you times with the charge, okay, of 1 electron. Okay, when you have that overall charge, 1 electron, they have 1.6 times 10 negative 19 charge. Now I have 2 moles times 2, and it's not only 1 electron. Okay, it's going to be for 1 mole of electron, and we need to know 1 mole got how many electrons. So they represent using L, which is your Avogadro constant, and that will result in formation of 63.5 gram of copper, which is 1 mole of copper. Okay, so that's your equation number 1. Your equation number 2 is resultant to what you have. Okay, 16200. Okay, 16200. It's going to deposit 5.09 gram. I just put 5.09 gram. Okay, so you have equation 2. Okay, what is the relationship? This and this, they follow the same relationship. So if you want to find, okay, the relationship between them, okay, it's the same. 1 divided by 2. Okay, it means that this equation, if you divide them with each other, okay, you are going to get equal. Okay, so it means that with when I put this, okay, when this one divided by this, 63.5 divided by this, okay, I can find out, okay, the relationship is going to be the same. I can find out what is going to be the L. Okay, so I just calculate what is the L. Okay, just calculate L, and you get this. Okay, I supposed to get 6.02 times 10 to the power of 23. Okay, but I'm not getting that. Okay, to explain why, I think because of the experimental error and the conditions and so on. Okay, but you are getting something closer to Avogadro constant. This is what we want. Okay, 6.32 times 10 to the power of 23. If you are not sure, okay, just WhatsApp me. I can pass you the investigation that I've done previously with you. Okay, the worksheet, I'm still keeping it. Okay, so you can also go through that. Okay, because it's the same. Okay, how do we predict Avogadro constant? Okay, using experimental data. Okay, this is the way. Yeah. Now, next question. Explain why magnesium metal cannot be obtained by electrolysis, okay, of dilute aqueous magnesium sulfate. We have done this similar question before. Okay, same. Okay, you have MgSO4. Okay, MgSO4, you have Mg2 plus and SO4 2 minus, and it's in aqueous, so you have H plus and OH minus. Okay, now we are talking about cathode. So there are 2 types of ions will go to cathode, Mg2 plus and H plus. Here at the anode, you know, basically which one will be discharged. Okay, the OH will be discharged. Why? SO4 2 minus is a very big very big ion, so they don't get discharged easily. So OH minus will be discharged. But that is not the question over here. They are asking, okay, why you don't get magnesium. So it means you have these 2 equations. Okay, the Mg2 plus will go there, and also H plus will go there. So I write down the equation. Okay, if let's say they got discharged, what is going to be the E value? Okay, the E value from the data booklet, negative 2.38, and the E value, this one is 0. Everyone should know about this. Okay, so when you compare them, okay, you will see that which one is more positive. You can see that this one, the H plus, is more positive. So therefore, okay, the H plus will receive electron to form hydrogen. Okay, in comparison to magnesium. So that is the one that is going to happen. Okay, this is what we call the H plus will be selected and will be it will be selected, and it will be when last time when you learn about electrolysis, okay, when you learn about cell electrolytic cell, why H plus is selected. Last time you learned according to reactivity series, Yeah, the H plus is lower, I'm selecting H plus, but this is the actual reason. Okay, this is the actual reason why H plus will be selected, because it's easier. Okay, it's easier to add electron. What is adding electron? So it's going to be reduction. Okay, reduction is gain of electron. Okay, so it means it's easier to reduce H plus compared to reducing Mg2 plus. Okay, that's the reason. Okay, that's the reason. So here, when you write down, you can write down hydrogen is produced instead. Okay, and you can also include, okay, the reduction of H plus is more easier, okay, than the reduction in Mg2 plus. So that is going to be what we are going to explain over there. Okay, so it's going to be more easier than you are trying to reduce the Mg2 plus. Okay, any question up to here? I will still record. Okay, you see here, I'm not going to write now. Okay, so you see here, explain what is meant by the following terms. Okay, what is going to be half-life of a reaction? Okay, what is half-life? Okay, half-life is the time taken, okay, for an amount or the concentration of the reactant to become half of its original value. Okay, so this one is taken directly from the marking key, but if you want to answer, I will just suggest you to answer it this way. Time taken for the amount or the concentration of the reactant to become half of its original value. Okay, to become half of its original value. Now, rate determining step. Okay, rate determining step is the slowest step in the reaction. Don't write slow step. Okay, I've seen some students write slow step. No, there are many slow steps. Okay, so you need to tell which one. Okay, so the slowest step. Okay, that will be the one that will be the rate determining step. Now, the reaction between hydroxide ion and bromomethane is first order. Okay, with respect to OH minus, and first order with respect to this. Okay, so now we are going to ask you to suggest a practical method that will confirm the reaction is first order. Now, this is very, very important. Okay, because when we learned about how do you do the practical method, okay, what are the practical method that we can use? Okay, remember about quenching and so on. Okay, so the one that we learned. Okay, is it continuous? Okay, is it going to be sampling method? Okay, you do not need to focus on the term. Okay, but they are asking you, okay, how you are going to do this. So here, the one that I can think of, okay, is it going to be continuous or sampling? I think I'm going to use the approach of sampling. Okay, I'm going to use the approach of sampling. But here, how do you confirm? Is going to be first order with respect of OH minus. Do take note, okay, CH3Br is also first order. Now, if you want to only focus on one, okay, you must make sure you use the excess CH3Br. Okay, if you use excess CH3Br, this will make sure that whatever results that you are going to get is only responding to OH minus. Okay, so that is going to be the first thing you need to take note. I am going to use several experiments with different concentration of OH minus. Okay, I'm not going to do continuous method. I am going to control the temperature, okay, so that everything is going to be the same temperature. And I'm going to measure the time, okay, the time for what? Okay, the time that I'm going to get the concentration, okay, to become, it means what is the time taken, okay, for the reaction to happen or to finish. Yeah, so here I'm going to find, okay, the concentration of the OH minus in sample. Okay, I'm going to find the concentration of OH minus in sample. And how do I find that? Okay, I'm going to titrate, okay, using something, okay, that can make me find out the OH minus. So maybe I titrate with acid. Okay, or you can use a pH probe. Okay, you can use a pH probe, or you can also find out the concentration of Br minus. How? You can find out by using silver ions. Okay, you can find out the moment the precipitate of AgBr form. Okay, that's going to be the concentration of Br. You can find out all that. whatever things that you have done over here, okay, we can process the results, okay, by plotting the graph of concentration, okay, against rate. Okay, we can plot the concentration against rate, and we try to, or you can try to evaluate the rate, okay, by using the table. If you can say that, okay, when you increase the concentration of OH minus double, if you can find out the rate become double, then you can say that this is going to be a first order. Okay, that is what they say, evaluate the rate is proportional to OH minus numerically. Or you can plot the result. If you plot the result, okay, you see when I plot the result, I even draw the graph here. I sketch the graph here. When you plot the result, okay, you are plotting against either concentration against time or concentration against rate. Okay, so if you plot against concentration against time, okay, we are talking about first order. Okay, first order, then you're supposed to have a curve. Okay, but the curve is going to be, there are two types of curve. Okay, one belongs to first order, second belongs to second order. That one you have to follow the half-life. Okay, if you can find out the half-life is constant, then it's going to be first order. Okay, if the half-life is going to be different, then it's going to be second order. Okay, or the best way is to draw the concentration against rate. Okay, the concentration against rate, the zero order is going to be the constant. Okay, the straight line, and then first order is going to be the straight line, the one that is starting from the origin. Okay, so that is going to be the first order, and then second order is a curve. So since we know it's going to be a first order reaction, we are expecting to get the straight line passing the origin. Okay, so that is what we are going to look for. So if you can explain all this, okay, and if you match 4 of these criteria that they are asking over here, then you will get the 4 marks. Okay, so please explain. But for me, if you ask me what is the most important points, this one, okay, very important. You are going to measure the time, yes. Okay, you are going to measure the OH, and we are going to plot the graph. Okay, and explain a little bit about the graph. You see, not so much. Okay, but I think you need to make sure that you mention that you are using excess CH3Br. Or sometimes the question will ask, why you need to use excess CH3Br? Okay, when you are doing this analysis, to make sure, okay, that the rate is only responding to concentration, change of concentration in OH minus only. Okay, that's going to be the answer. Okay, so you are going to actually eliminate. Okay, you are going to eliminate the changes involving CH3Br. Okay, so that's going to be the practical methods. Okay, so now I will start writing. So here you see they say the hydrolysis, okay, of methyl ethanoate, okay, with hydroxide ion is the first order. Okay, and that first order with respect to OH minus also. So they are asking, okay, they are asking that the rate of reaction is given. So we just put in, okay, the rate equation. So K, CH3, CO2, CH3 and everything, you just put it over there. And then you, the question is you need to calculate the value of K. Okay, so you can see my calculation over there. Okay, you can have a look. Okay, but anyway, I will see the chat. Okay, Justin has a question. Okay, sir, I got a singular question. Okay, and the answer was does not change or change slightly. Justin, can you explain more? Justin? Oh, for why it is going to be excess. Okay, so this one, okay, when you put something in excess, okay, when you put let's say for example, okay, if I know X and Y, okay, when I put in this reaction, okay, and then you are going to, we know that Okay, x plus y plus z to give you something. And I know that x and y, okay, both of them, they are going to be involved in the rate equation, for example. Both of them are involved in the slow step, for example. So when I have that, okay, both of them, they are going to change accordingly. Okay, so how do I just focus on identifying the changes involving x only? Okay, so what we can do is, okay, we can increase the concentration that y. Okay, you try to increase the concentration of y, and we can try to when you do that, you are eliminating, okay, you're eliminating the influence, okay, the influence of y when it comes to the rate of reaction. Okay, so it means that we are just focusing, or just, I think the chances of the x changing and affecting the rate is going to be just depending on the x alone, and it's not depending on y because it's in excess. So it means we know there's a lot. Okay, so we eliminate, okay, the y. So if you are going to test only for y, then what you need to do, you need to make this into excess. Okay, so it means what the reason is why we don't want to have any changes related to the y. It means we are trying to eliminate the effect of that one reactant towards the rate of reaction. Okay, but you can read more about this, Justin. Okay, read more about this. But this one is one of the in the practical, we always put excess. Okay, and when you put excess, the concentration and then the relationship to the rate is going to become constant. Okay, it's going to be constant. Yeah. So basically, to make the concentration constant, so it doesn't affect the rate. Yes, correct. Okay, that's the answer. So we want to make the concentration constant. Okay, so the rate will be constant also for that. Okay, so that's the explanation. Okay, that's the explanation. Okay, next. Okay, if we move on. Okay, number 3. Okay, ammonium chloride. Okay, dissolve in water to make an acidic solution. Okay, so calculate the H plus. So they already gave you 4.89. pH is 4.89. Okay, use the formula. Okay, 10 to the power of negative 4.89, yeah, not 10 to the power of 4.89. Okay, please use that. 3 significant figures. Okay, you have H plus. Calculate the pKa value of ammonium ion. Okay, so ammonium ion, okay, Ka equals to concentration of ammonia, concentration of H plus, divided by concentration of ammonium. Okay, but take note, these two concentrations are the same. Okay, so we are taking it as H plus to the power of 2. Why? Because ammonia, okay, ammonia concentration is the same as concentration of H plus. Okay, so you have this formula. And this formula also, there are assumptions. Okay, what are the assumptions? The dissociation of ammonium ion, okay, is too little. Okay, it's too little until we only use the initial concentration. Okay, so we use that formula for pKa. So H plus we have calculated, just put the H plus over there. And then ammonium ion, okay, they already give you 0.3, just put 0.3. Okay, and then you get the answer for Ka. Once you have the Ka, pKa is negative log Ka, you get 9.26. Now, I want you to focus on the assumptions. Please remember this, okay? They normally don't ask, okay, but there are high possibilities where they will ask about this. Okay, what are the assumptions? Okay, the assumption is, okay, we are going to assume that this is going to be the same. Okay, and then we are going to also assume, okay, the dissociation is too little until we use the initial concentration of ammonium ion. Okay, so that will be the assumptions. Okay, now, so you calculate, you get 9.26. Now, a buffer solution can be formed, okay, by mixing ammonium chloride and ammonia solution. Explain with the aid of equation how this one can behave as a buffer. So I write down the equation also. Then you how to explain, you please explain yourself. Yeah. So H plus, okay, when you add H plus, it will react with the base. The base is going to be ammonia, and then you are going to get ammonium ion. Okay. Now, if you have OH minus, okay, if you have OH minus, it will react with the acid. Okay, the acid is going to be the NH4 plus, and then you are going to get ammonia and this. Okay, it's still okay if you write OH minus plus H plus to give you water. Okay, but I will suggest you to use this equation instead. Okay, because it will show us that there is a buffer. Okay, so please take note of that. Okay, and then explain. Okay, so when OH is removed, okay, there is no change in pH. When H plus is removed in that way, there is no pH. And then because there's ammonium ion, there's so many ammonium ions. So the changes that happen over there, okay, will not be because it's too much, in excess. So we are not going to change much. Okay, something like that. Okay, the same thing, whatever ammonium ion that is being used, when they decrease, it's not going to affect the overall concentration. Okay, now use the value of Kw. Okay, Kw, okay, you should know Kw is H plus and then OH minus. Okay, and then this one is the same, so we always use this formula for Kw. And this value you need to memorize here. Okay, 1 times 10 negative 14. Okay, pure water. So when you have this, okay, H plus is 1 times 10 negative 7. Okay, this is going to be the answer. Now the pH of pure water is going to be, you see, different temperature. Okay, you are going to have different pH. Okay, so we need to calculate the Kw at 50 degrees Celsius. Okay, so how to do that? Okay, so they have given you the pH. Okay, just use the concentration. Just use the calculate what is going to be the concentration of H plus by using the formula. Okay, just use 10 to the power of negative 6.64. You will get the concentration of H plus. Then we use the formula. Okay, use the formula, and then you will get the Kw. The new Kw is going to be this one. Now, do remember Kw. Okay, at normal condition, the standard condition. Okay, it's going to be always 1 times 10 negative 14. Okay, but when you increase the temperature, okay, to 50, you can see the Kw now is going to be more, okay, than what you have at the standard condition. Okay, this is why, okay, because, okay, if you follow H2O, okay, to become H plus and OH minus, there will be delta H. Okay, so I want to ask you now, okay, that delta H, okay, based on the information that you have now, okay, 1 times 10 negative 14 and 5.25 times 10 negative 14, I want to know, okay, whether your enthalpy change over here, is it positive or negative? Victoria? How to predict the enthalpy change for this reaction? Is it positive or negative? Using the information of the Kw. Your Kw is increasing. Okay, it means it's moving forward. Okay, when it moves forward, this is going to use the LCP principle. Okay, the temperature earlier 25 degrees Celsius. When you increase temperature increase, suddenly it's moving forward. So how to identify? Just see, when this is positive, this is going to be cold, this is going to be hot. So when I increase the temperature, okay, I need to decrease the temperature. How do I decrease the temperature? By favoring towards cold. Okay, so you can see here, okay, it's favoring to the right. So here we say the temperature, higher temperature, okay, favors endothermic reaction. I hope you still remember this. Okay, temperature increase, it favors endothermic reaction. So the position of the equilibrium moves to the right. That's why the Kw increases. So if I ask you to predict, this is going to be positive. Okay, this is positive. So this is by using this information that you have. So it means that on top of this 1 mark and 2 marks, okay, I can give you another 2 marks. Okay, if I design a question, okay, predict okay, the predict what is going to be the enthalpy change, okay, for ionization of for this, okay. So the equation, okay, predict then and then give reason, okay, give reason. So I can say based on what I said just now, okay, you just tell, okay, it's going to be endothermic, okay, and then why, okay, temperature increase, it favors endothermic, your kW increasing, okay. So once you relate that, I think even 3 marks it can still go, okay, and it's still it's a level 3 question, okay. So you can also refer to that, okay. But anyway, let's move forward, move on. Okay, number 4, okay, the table shows some standard entropy data, and then I need to calculate the entropy change for this reaction. So this one quite simple, okay. This is going to be entropy of product minus the entropy of the reactant, okay. So please remember the 2, so you need to times 2 times 69, okay, then oxygen, okay, 205 minus the reactant, so make sure you times by 2 also, you will get positive 189, okay, positive 189, but be very careful, it's joule, okay. Now use the value, okay, to calculate the temperature at which this temperature, this reaction will become feasible. Now this reaction will become feasible normally when your Gibbs free energy become negative, okay. But if you want to use this formula, then you need to use the Gibbs free energy equals to 0. Then only we can find out what is the temperature, okay. So the temperature when it becomes feasible, okay, or the temperature when it becomes 0, okay, is going to be at this temperature. And how do I use that? Then you need to use this formula, Gibbs free energy formula. Okay, if you remember how I asked you to remember, okay, or you have your own way to remember, please remember that. Okay, Mr. Gopi, is not too hot. Okay, so I just put not, then HOT, then I just put S. Okay, so something like that. Okay, just remember. Figure out a way to remember this, okay. So once you have that, okay, the important thing is writing this in a proper unit, okay. So here I'm going to use, okay, the joule only, okay. I'm going to use joule only. So 118, okay, you can see 118, where do we get this? Okay, it's from here, okay, kilo, so times by 1000, okay, you have this, minus the temperature that I'm looking for, must be in Kelvin, okay, and then you have this 189, okay, it's going to be joule, okay, no need to change, you already changed the enthalpy change already, okay. Then calculate the temperature and you will get 624.34. Okay, you can give your answer like this. Normally I'll suggest you to give in this form, 624.34, or it's fine to write down as 624 Kelvin, is still fine, 3 significant figures, okay. But if in the question they say must use 3 significant figures, then must use 624, okay, must use 624, or must use 2 significant figures, okay, the answer will be 620, okay, that's going to be 2 significant figure, okay. So please adjust accordingly. Yeah. Now solid, okay, lead-2 oxide can be made by heating lead metal in air. So I wrote the equation Pb plus O2 to give you PbO2. So solid, gas, solid. So predict the sign. Okay, so when I see here solid, gas to become solid, it means this is ordered, this is less ordered, then everything become ordered. So it means that it is going to become overall everything is getting ordered. So if it is getting ordered, it means your sign of the entropy change is going to be negative. Okay, what is entropy? Is a measure of randomness, okay, or measure of disorder. So when everything becoming ordered, we don't like, so we just put negative over there. But when they ask you to explain, you don't explain, or they are ordered, less ordered, now become ordered. No, you just explain. How do what is the conclusion that I'm getting? Oh, I see this one is going to be oxygen gas. So it's less ordered, but now no gas. Okay. So you can just focus on the gas. Okay. You can say that decrease in number of gas molecules because there's no gas over here. Okay. Because of that, okay, your sign, okay, this is going to be what is expected from you. Okay, there is no decrease in number of gas molecules. If you happen to give some other answers, I think they will consider. Okay, I think they will consider. But try to use this method. It means that when you don't see gas, okay, just say decrease in number of gas molecules. Okay, if you see all of them are going to be in gaseous form, then you look at the total overall number of molecules and so on. Please decide which one is the best. Okay. Okay, that one I leave it here. Okay, so number 5 now. Okay, I think we can finish 5. Okay, completely today. Now, for number 5, okay, describe fully what will be seen, okay, when magnesium and strontium are heated separately in oxygen. Now, this is a AS concept. Okay. Now, Gabriela Nicole was asking, cannot say decrease in randomness. You can say decrease in randomness, Gabriela Nicole, but they don't want to see that. What they want is decrease in randomness. How? Okay. It means they're still asking another question. Why there is a decrease in randomness? Okay, because the number of moles of gas are going to be decreasing. So you need to still answer the basic question over there. Okay, so this one, okay, coming back to question number 5, this is going to be a group 2 metal question. Okay, now you can see here, okay, this is going to be a combination of group 2 and your lattice energy chapter. Okay, because normally group 2 they're definitely going to ask you about lattice energy. Okay, so you can see here, okay, they can ask you a lot of things even in AS. Okay, so you see magnesium, okay, heated separately with oxygen, they will give you magnesium oxide, strontium oxide. Okay, write the equation, but they want to see described fully. So this is not what they want. Okay, they want to hear this one. Now this reaction, okay, both any group 2 metal, okay, when they burn in oxygen, the oxide is going to give us, okay, the white solid, magnesium oxide, okay, barium oxide, strontium oxide, they are all white solid. Okay, so you need to say white solid is formed. You can say that the reaction is a bit slow, and then the reactivity, because as you go down, okay, the reactivity will be more reactive, more vigorous. But I don't think so. When I checked the marking key, they didn't give answers for this. What they were focusing on, the flame. Now you can see in your AS book, they say bright white flame. If you write white flame, it's also okay. But strontium, okay, they are going to be so vigorous and they will give you a red flame. Okay, that is what they want to see over here also. Okay, it burns, okay, in bright white flame to give you white solid. So for strontium, it burns with red flame to give you a white solid. Okay, so please adjust accordingly. This is from your AS. Okay, write an equation for each of the following process. Include the state symbols. Calcium burn in air, okay, Ca plus O2 to give you calcium oxide. Okay, so balance it, okay, and then write the equation. Okay, calcium oxide is solid. Yeah. Now calcium carbonate is heated strongly. Now this is going to be decomposition reaction. Okay, for carbonate, it will give you calcium oxide plus carbon dioxide. Okay, so you just write down over there. Okay, so it will give you solid. This is gas. Okay. Now, calcium hydroxide, okay, is formed when water is added to calcium oxide. Okay, when water is going to be added to calcium oxide, you are going to get calcium hydroxide. Okay, calcium hydroxide. Okay, okay, this one I hope you remember. Yeah. Okay, before I go further, this is going to be limestone. Okay, calcium carbonate, another name is limestone. Okay, and then calcium oxide, okay, is going to be lime. Okay, so this lime, okay, when you add with water, okay, you are going to get quicklime. Calcium hydroxide is quicklime. Now quicklime, okay, can be in two forms. Okay, If you have calcium hydroxide, okay, in form of solid or powder form, we call it slaked lime. Okay, but quicklime, okay, do remember, quicklime is going to be also known as lime water. Okay, when we use to test for carbon dioxide. Okay, so please remember these terms and so on. Okay, describe the main benefit of adding calcium hydroxide or calcium carbonate to the soil. So basically what we are trying to do, we are trying to increase the pH. Okay, so or we are trying to reduce the or neutralize the acid. Okay, neutralize the acid in the soil. You bring up the pH. Okay, you bring up the pH. Okay, so sir, isn't the calcium oxide supposed to be in solid state? It is solid. Maybe it looks like a, okay, so it's solid. Okay, solid. This is gas. Solid. Okay, so solid, and then carbon dioxide is gas. Okay, calcium oxide is always solid. Another way to remember, all group 2 oxides, okay, they are white solid. Okay, you can just remember that. Now, explain why group 2 hydroxide become more soluble in the group. This one, I'm very tired to explain the same thing again here. Yeah, so please refer to the notes or the video that I made earlier. Okay, but this one is going to be the SHL. Okay, so why group 2 hydroxide become more soluble? So we are looking at your enthalpy of solution, okay, to become more negative. Okay, so more exothermic. So how can you achieve that? Okay, if it is hydroxide, I told you the lattice energy, the decrease in lattice energy is going to be more than the decrease in your hydration. Okay, because of that, okay, that will make the enthalpy of solution to become more negative. Therefore, it's more soluble. Okay, so please remember, for sulfate, it's going to be the other way around. So for sulfate, it's going to be using the SHL also. Sulfate, the decrease in hydration is going to be more than the decrease in lattice energy. So please refer to that. Okay, please refer to that. Okay, so I'll skip this part. Now describe the observation, if any, okay, that you will make when you are adding sodium hydroxide to barium chloride. Okay, when you do that, barium hydroxide, and then you are going to get sodium chloride. Both of them are colorless. Okay, so you don't see anything. Okay, so you can say no change. Okay, no change. There's no observation. When you add few drops of sulfuric acid and barium chloride, this one you must see something, because if let's say there is a chemistry student do not know about this, okay, it's going to be something that is very alarming. Why? If you study chemistry, every student must know, okay, the moment you get barium sulfate, okay, and then you have ACR, whatever, the moment you have barium sulfate, this is a white PPT. You must know this. Okay, you must know this. So definitely you'll get a white precipitate. Okay, see. Okay. Now explain, okay, and describe how thermal stability. Now this thermal stability not only for carbonates, okay, it is also for sulfates. It's also for hydroxides. Okay, it's the same. Yeah, thermal stability of group 2, when you go down the group, okay, thermal stability increases. Okay, or it means that you need higher temperature, okay, to break the bond. Okay, and we have learned about it in A2, okay, by finding out the relationship with that. Okay, so group 2 generally carbonates, they are very big, more large anions. Okay, and then we have group 2 ions. Okay, group 2 ions, when they go down, the ions getting bigger and bigger. Okay, they're getting bigger and bigger. So we need to talk about the ionic radius, okay, or the cationic radius. Okay, so you can say as you go down, okay, the ionic radius of the cation, okay, they will increase. Okay, when they increase, the charge density is going to be lower. Okay, when it is lower, okay, it do not have enough polarizing ability. Okay, or less polarization as you go down the group. And when you don't have a lot of polarization, there won't be any distortion, okay, of the electron cloud of the carbonate. Okay, when there is no distortion, okay, or when there is no polarization, okay, the bond, okay, between the carbon and oxygen, okay, in carbonates, it remains strong. It is not going to become weak. Okay, so it is going to be harder to break those bonds. Okay, so as you go down, it will become more thermally stable. Okay, whatever that I mentioned over here related to size, related to polarizing power, and then you need to also mention about the, after you talk about polarizing power of the cation, you need to talk about the distortion of the electron cloud of the anion. Okay, then you summarize it. Okay, so that is going to be the one that I want to discuss for today. Okay, the first part of this lesson. Okay, for copper 2 sulfate solution, okay, copper sulfate undergoes visible changes with certain regions. Okay, therefore, okay, for this one, okay, I wrote a lot of notes over here so that we can learn. Yeah. So here you see these are the part that where sometimes I told you, okay, they certain things you need to memorize. Okay, so sometimes, okay, for those who have revised this chapter by heart, then it's going to be very useful. Okay, because why? Okay, in this particular year, okay, they ask 4 marks. Okay, but for me, if you ask, yeah, 4 marks is considered to be too little. Okay, too little for the effort, okay, that you will take to memorize all this. Okay, so therefore, okay, I will just suggest, okay, just learn things by heart now. Okay, but be ready. Okay, be ready to accept the fact that, okay, maybe you won't if you don't have time, okay, to memorize all this. Okay, be ready to let go certain number of marks. Okay, so but here, okay, as a teacher, okay, what I can tell, okay, I can tell that, okay, please remember this. Please remember this. So it depends on how you want to take it. Okay, like for me, okay, let's learn. Okay, let's learn if they ask questions on this. What are the things that you need to remember? What are the things that we need to really focus? Okay, like whenever I have this copper sulfate, okay, copper sulfate means copper sulfate is in the form of CuH2O6, okay, and then 2 plus. So now when I add a few drops of ammonia, what you need to remember, okay? The thing that you need to remember when you just add few drops of ammonia, and the difference between the when you're adding excess of ammonia is going to be, we are going to assume a few drops of ammonia. We are going to assume there is no ammonia. Okay, just assume you are not adding any ammonia. Okay, you are going to have, okay, because it's ammonia solution, okay, you are going to have the water itself will give you the OH minus. The ligand that we are interested when you add few drops of ammonia will be the OH. So I want you to think as though they are adding OH minus. Okay, as though they are adding OH minus. So what do you see, okay, when you add OH minus over there? Okay, you will see a pale blue precipitate. Do remember this, okay, pale blue precipitate. So it means this reaction is the same as you are adding excess sodium hydroxide. Okay, I want you to remember this. Okay, this reaction is the same as you are adding excess sodium hydroxide. So you will get the pale blue precipitate. And the equation is also going to be the same. Okay, what is going to be the equation? The equation is going to be something reacting with OH. So this is the equation, okay, plus OH minus, okay, there is going to be a Ligand exchange over here, where you are going to remove 2 moles of water, and you are going to get this, okay. Do remember there is no charge, okay, because OH minus is -1, Cu2 plus, so you have 2 negative ones, and then it will cancel, and it will give you the solid. That's why it's a precipitate. Okay, it's a ligand displacement reaction. So if they ask you identify the formula of the complex ion that is formed, or the one that is responsible to give you the pale blue precipitate, it's going to be the copper CuOH2 H2O4. Okay, or if you give your answer as CuOH2, it's still accepted. but I don't want you to remember this. Okay, I don't want you to remember this because it is copper hydroxide is copper hydroxide with 4 ligands of water. Okay, please remember that. Okay, so I want you to remember the moment we see the copper, okay, the one related to precipitate. Okay, the precipitate, which is the pale blue precipitate, they are going to be the copper hydroxide, CuOH2. Then do remember, include the water, which is going to be 4 moles of water. Okay, so that is going to be the one that is going to give you the pale blue precipitate, and the answer is going to be the same over here. Okay, that is going to be the one responsible. It means, do remember, when I add few drops of ammonia, when I add excess sodium hydroxide, okay, to copper 2 plus, the reactions are the same. This is what I want you to remember. Okay, the reactions are the same. Now, if let's say I'm going to add excess ammonia, what is going to happen? Things are going to be different now. Now, if you add excess ammonia, okay, in your textbook, you will see this. This is going to be when you get, okay, let's say when you have the hydroxide, sodium hydroxide, once you get this solid, when you add with the ammonia, you are going to get a deep blue solution. Okay, deep blue solution, but this one, be careful, you are starting with this. Okay, but we are starting with this. So it's the reaction is almost the same, but when you write the equation, let's say they ask you to write the equation, it means that you are replacing out of this water, 6 moles of water, you have to replace 4 moles of water, replace it with ammonia, and then the water molecules, the 2 water molecules will stay. It means our end product is still the same. So we are assuming, okay, what do we assume? Just take it as these 2 equations joined together, okay, and then you cancel the pale blue precipitate. Okay, but okay, if you want to put it together, I've written over here. If you want to put it together, okay, it means that copper CuH2O6, okay, when I react with ammonia, okay, I am going to get, okay, do remember this one in the next page of the textbook, yeah, they mentioned that when you add drop by drop, okay, what is going to happen? You are going to have this displacement of the ligand, replacement of the ligand, substitution of ligand, sorry. This substitution of ligand, it happens step by step. Okay, it happens step by step. So if you are using excess, okay, do take note, this is excess. Okay, so this one is not few drops of NH3. Yeah, so this one is going to be as they are reacting, you are going to get this, then you are going to get this. Okay, but in total, okay, if I just put it over here, if I highlight here, this is what we are interested with, which is the same as you combine these 2 equations. Okay, it's quite the same. So it means that if you're having it in excess, you are going to get ammonia, 4 moles of ammonia, and then 2 moles of water. Okay, so that is going to give you, okay, do remember the moment you see 2 plus, it's going to be aqueous. And what is that? Okay, this is going to be deep blue solution. Okay, deep blue solution. So it means that, okay, whenever you have pale blue precipitate, remember CuOH2 H2O4. But if it is deep blue, okay, it means the ammonia, the 4 molecules of ammonia have formed 4 dative bonds, okay, to that molecule, leaving this. Okay, then the only thing that you need to remember left with Cl. Okay, this one is quite easy. Okay, Cl minus, okay, whenever they react with this copper, the complex ion of copper, okay, they will give you yellow solution, not yellow precipitate. Yeah, the precipitate can only for copper hydroxide. Okay, do remember copper hydroxide can be also written in this form. Okay, this one I already told you earlier. So here, okay, the yellow solution, okay, is going to be represented by CuCl4 2 minus. Why CuCl4 2 minus? I think Cu2 plus, Cl minus, Cl minus, Cl minus, Cl minus. Okay, so you join this one and all this, you will get -2. Okay, that's a charge. Okay, so I want you, okay, to really look into this, okay, because I have written for you all the reactions, okay, involving this copper, okay, copper ions, okay. Even here, the full equation I have written for you, okay, you can have a look, okay. But what is important over here is, okay, if let's say you don't remember the equations and so on, what is the one that I really want you to remember is when you add few drops of ammonia, you think as though you are adding OH minus. This is what I want you to remember. Okay. So it means the reaction of adding few drops of ammonia is going to be the same as you are adding excess sodium hydroxide. Okay, so you are going to get a pale blue precipitate, and that pale blue precipitate, you know, you should know what is that. Okay, you should know what is that. The color also and so on. Okay, this one I'll leave it to you how you want to remember. Okay, but I'll pass you these notes. Okay, once it's done. Yeah. So remind me. Okay, if I forget to pass this to you. Yeah, if you need these notes. Now, next. Okay. Of course, in our syllabus, okay, if you're asking, sir, is this the only thing that I need to remember? No, not really. Therefore, there is cobalt. Okay, it's related to cobalt. And this question was related to cobalt. And I was surprised why suddenly they're asking too many about copper and then cobalt. Then I went and checked in my book and so on. I came up with all the notes. But later, only when I read the question, I saw, oh, they do not want the equation. What they want is they are trying to relate the color, okay, the change of color, copper to chloride. It changes from blue to pink. Okay, we need to explain this observation, but no need equation. So it means whatever things that I wrote over there is actually extra notes for you. Okay, but you need to include you need to include the reference of electron movement between the orbitals. So this one, when they mention about including the electron movement from orbitals and so on, that is already it's already indication, okay, saying that they want to see the why there is a difference in color. So you need to talk about the d orbital splitting, okay, or the non-degenerative orbitals, okay. So the answer, okay, let me discuss the answer first, okay. Why there is a color change from blue to pink? Okay, definitely there is going to be something to do with the ligand exchange. What ligands that are involved? Chloride, okay, Cr minus, and then water. Okay, these are the two ligands that are involved. Okay, so there is a ligand exchange. Because of this ligand exchange, even before, okay, even before, presence of ligand will create the two sets of non-degenerative d orbitals. Okay, so they already created. So you no need to tell suddenly now it starts to split. No, you just need to explain that the moment you have different ligand, the magnitude, okay, the magnitude of the the magnitude of the energy, okay, the magnitude of the energy of the non-degenerative orbital, they are going to change, okay, because different ligand. So they already splitted, but now it's going to change a little bit. Once you have that, when you pass through, when you pass light, okay, when you pass through the visible light, okay, this will change, okay, the light, the amount of wavelength or the energy that is going to be absorbed by the electron, okay, from the lower energy, okay, when they are going to absorb and they become excited to go to the d orbital, okay, that has higher energy. So so that you are going to give you a complementary color, okay, to the light that is going to give, okay, after passing through the sample. So because of that, you are going to have different color. Okay, so here what are the points that they are looking for? They are looking for ligand exchange. They are looking for the magnitude of the d-splitting is going to be different. Okay, then the changes of wavelength of the light that is being absorbed, and you need to mention about the electron being excited. okay, from lower energy to higher energy. And then the complementary colors now will be different because different energy is going to be absorbed. Okay, so that is going to be what you answer. Okay, but I want to discuss this because we started about the equations. Okay, let's start with the cobalt. Okay, cobalt 2 plus. Now cobalt 2 plus, they always exist, okay, in this form. Okay, they always exist. Okay, they always exist in this form. Cobalt 2 plus, they always exist in this form. And the color is going to be always going to be pink. Okay, the color is always going to be pink. When you add, okay, when you add hydroxide ion, sodium hydroxide and so on, you are going to have, okay, a situation where they are going to give you this, okay, CO, OH2 and water. This is not something that looks new. You can see here, similar to the copper. Okay, when you add, you are going to get something similar to copper also. Okay, so nothing special. Okay, but the color, okay, the color, they didn't mention it in the textbook. Okay, the color didn't mention it in textbook, but they mentioned that when you warm this, okay, it means when you heat up this, you are going to get a red precipitate. Okay, they said if you warm this, then you are going to get a red precipitate. Now, what will happen? Okay, what will happen if you add ammonia? Okay, what will happen when you add ammonia? This is excess ammonia. So even this one, if you are adding ammonia drop by drop, little ammonia, you are going to get this condition also. Please remember this, okay, like what I said. Okay, but now if you are adding excess ammonia, you are going to get this. Okay, you are going to get this. And if you are adding, okay, if you are adding excess chloride or HCl, okay, you are going to get this, which is going to be a blue solution. Do remember, they are all pink in the beginning. Okay, they are all pink in the beginning. Okay, they are all pink in the beginning, but now they are going to become blue. This one, please check. Okay, if I'm not mistaken, it's straw in color, I think. Okay, something like a yellowish brown kind of color. Okay, but again, here, okay, it's going to change into blue. But coming back to the question, they say that when I add cobalt to chloride, it means cobalt to chloride, they are talking about this. Okay, they're talking about this, which is going to be blue in color. When I add water, I am going to get a pink color solution. So it means that the water is exchanging with the ligand with the Cl. So you are going to get this, which is coming back from here to here. Okay, which is going to be the pink color. So these are the things, okay, basically that I want you to remember, okay, memorize better, okay. But again, this one, I leave it to you as a capacity of a student. If you have that capacity to memorize this, then go ahead. Okay, if you want to skip that, I cannot blame you. But okay, I want you to focus. If let's say you want to study, you just want the basic stuff. What are the things, important things that you need to know? I have told you what are the important things that you need to know. Okay, that's why I'm spending more time over here. Okay, so if you want to know, you want to make sure that you don't lose these 4 marks. Okay, you don't want, you can't afford to lose that 4 marks, for example. Then you need to focus on this. Okay, but nobody knows, okay, how it's going to be asked and so on. Okay, we won't know. If the question doesn't specify reference to electron movement, can we use LCP? Okay, if let's say they don't specify, can we use LCP? I think can, okay, because it's supposed to be like this. So when you add water, so from blue to pink, so this one, blue to pink, more water, so you dissolve, can, but I think you still need to talk about ligand exchange also, Gabriel and Nico. Okay, so you cannot ignore the ligand exchange. Okay, but normally, okay, explain that it dissolves. Okay, explain it dissolves, yes. Okay, but do remember the equation is important. Here, no equation is needed. So you need to, if you are using the LCP, yeah, you need to write down the equation. But when you write down the equation, you still mention it's going to be ligand exchange. That cannot be said just dissolve. It's not enough. Okay, so you need to mention it's going to be a ligand exchange as well. But yes, okay, to answer that, okay, if you don't need to have any electron movement, it means you just want to explain just like that. Yeah, ligand exchange is going to be the main idea then. Okay, that will be the main idea. But equations are important if you are using the ligand exchange. So it's quite tough, okay, to remember. Okay, I do understand fully. Okay, but this one I leave it to you. Yeah, so nobody said it's going to be easy. Yeah, especially the one that requires things to memorize. Okay, there's a lot of things. Okay, but my work is to tell that there is a way to memorize it systematically, which I'm actually helping you over here. Okay, so the one that I want you to remember is going to be the precipitate. Okay, the precipitate, which is going to be the one I highlighted here. Okay, pale blue precipitate, pale blue precipitate. So all these are coming from where? Okay, it's coming from, okay, when you replace, okay, the 2 moles of water, you replace with OH. Okay, so that is going to give you the pale blue precipitate. Okay, please remember this. Okay, now, so next, okay, when chlorine gas, okay, is going to be bubbled in FeSO4, okay, the color of the solution changes from pale green to yellow. Okay, it means that pale green, I know that is going to be something related to my Cl2. Okay, something related to my Cl2. Now it's going to become yellow. Okay, so if I have something related to Cl2, it become yellow. So one thing that I can think of, maybe the reaction will continue. It is reacting with FeSO4. Okay, it is reacting with FeSO4. If it remains, yeah, green, then no reaction. But this one, there is a reaction. So Cl2 must be, if you have Cl2, definitely they will change into Cl minus. So I can see that, okay, if Cl2 changing into Cl minus is going to be receiving electron. So if this is receiving electron, okay, this is going to be reduction is gain of electrons. So this is reduction. So if this is reduction, okay, it means that this is a very good oxidizing agent. What is the definition of oxidizing agent? Something that can oxidize others, but they will themselves will undergo reduction. So it means that the Cl2 will be able, okay, will be able to oxidize. So how to oxidize? You see Fe2 plus. Fe2 plus oxidize to become Fe3 plus. That will be the one that is happening. So all this will help me to determine which equation should I use when I refer to the data booklet. So I know that, okay, this is the equation that I need to refer. But if you're not sure, yeah, you can actually bring in and write down the 2 first. Okay, bring in and write down 2. But you need to select which one, okay, because there is Fe2 plus to become Fe, okay, and there's also Fe3 plus to become Fe2 plus. So which one should we choose? So I chose, okay, this one because I know that, okay, if Cl2 is changing to Cl minus, because I'm talking about there is a reaction. Okay, if there is a reaction to become Cl minus, don't tell me that they are going to join with the solid. Impossible, right? Where the Cl minus joining with the solid. So it must be something that is having the Fe2 plus. So that's going to be another reason why I selected that equation also. Okay, so I wrote 2. Okay, I'm not sure. Okay, but I determine. Okay, I determine which one. So I determine, okay, once I have, okay, this will happen. Okay, then the use the data, okay, include an equation. Okay, include an equation, it means only one equation. So I put it like this. Okay, 1.36, this will move forward, this will move backward. So I just rearrange this. Okay, and then I can join them together, okay, by writing Cl2 plus 2 Fe2 plus. Why? I want to eliminate the 2 electrons. Okay, so it will give you this and it will give you this. Okay, so done. Okay, this one's done. You can write the same thing over here. Okay, because if you are wondering what happened to the SO4, okay, SO4 is going to be the what we call as spectator ion. Okay, SO4 is a spectator ion. So even if I write down like this, okay, SO4, then I have the 2 SO4 here. Later, what I will do, okay, I will remove the spectator ion. Okay, so I will eventually get Cl2 plus 2 Fe2 plus to give me 2 Fe3 plus 2 Cl minus. I think eventually I will also write it in this way. Okay, so how to know it is Fe2 plus, Fe3 plus, or Fe2 plus for the equation? So Shane, this one is quite simple. Okay, you see, Cl2 is reacting to Fe2 SO4. Sulfate is 2 minus. Okay, so I know Cl2 is reacting with Fe2 plus. So I know that there is a color change. It means there is a reaction. So if there is a reaction, I know maybe it will change into Fe3 plus, or it will change into Fe alone. Okay, I know that. Okay, but okay, I also need to know that Cl2 must also react. Okay, so Cl2 must react, okay, to give you something. So if it is reacting, the only thing that it will give is going to be Cl minus. So Cl minus must be bonded with something. Of course, Cl minus will not be bonded with the solid. Okay, so that is how I reach to the conclusion. It's supposed to be Fe3 plus and the Cl ion. So you get FeCl3. Okay, so in a simple terms, okay, so basically I'm thinking about, okay, Cl2 plus this is going to give me this. This is what is my thinking. Okay, I'm looking into this situation. Okay, so I already decided FeCl3 is going to be formed. Okay, based on whatever data that I have, I know this is going to be the one that is going to be formed. Okay, next. Can Shane, does it answer your question? Okay, she said, okay, sir. Okay, fine. So if a solution, okay, of chloride ion is added, okay, equilibrium is going to be established. Okay, so write an expression of stability constant. So stability constant, very important thing is to ignore this water. Water is constant. Yeah. So ignore the water. Okay, so when you write down, okay, you write down FeCl4, okay, minus, okay, divided by FeH2O 6 3 plus to the power of 1 times Cl minus to the power of 4. Okay, that's going to be my stability constant. For the above equilibrium, the numerical value is given. So just replace with that value that we have, 0.08. Okay, replace. FeCl4, okay, they say 0.1. Okay, put. And then they are asking you to calculate this concentration. So I just put it as X. Okay, X. And then this one is going to be concentration of Cl minus is going to be 2. So just put 2 to the power of 4. 2 to the power of 4 is 16. Okay, so I just calculate what is X. Okay, when I calculate the X, I'm going to get this. So what I want is I'm just simply looking for 0.07813 significant figures. Okay, move them here. Or you can say 7.81 times 10 negative 2 mole diameter. Very easy, yeah? That's why it's 1 mark and 1 mark. Okay, they didn't actually really want to focus on this. Okay, so if you are wrong with the water, I think most likely you will get wrong here. But okay, you if you take the water in, you will be wondering what will happen here. What should be the value that I should be using for water? Okay, so I think the moment you have that situation, then double check again. Okay, this is also can be another way to double check. Okay, but don't simply leave it empty. That is going to be something that is going to be wrong. Okay, sometimes, okay, you will get 0 for this, but you can still get 1 for this, even though it's wrong. Okay, the second part. Okay, as long you follow, okay, you included water, okay, fine. But you need to tell me why the water, okay, that you have included, you took that value, okay. But I don't think so there is any value related to the water. Even you try to include the water here, okay, even though I give you wrong here, okay, but if you try to include water here, you need to explain from where you get this water's concentration. If you cannot explain, then you won't get the marks. Okay, but anyway, just try. Okay, just try. Okay, so you might get the marks if you just keep on trying. But don't simply whack and then don't simply give answers just like that for the sake of showing that I don't know whether it's correct or not. But if I write a lot, maybe people will think that I'm putting in a lot of work. Yes, people will appreciate your work. Okay, but that doesn't mean that they will give you mark. Okay, so please remember that. Okay, so try to make it as systematic as possible. Do not need to include things, okay, that are not going to be tested, that are not being, they are not, don't include things that you shouldn't be including over there. Like for example, here, I'm including here because I want you guys to learn, okay? But if you go and include this, it's not going to do any good for you, okay, because they didn't ask about this. Okay, next. A polymer P can be made of the monomers, okay, of this benzene 1,4-diol chloride and benzene 1,3-diamine. Okay, draw a section of polymer chain of P. Okay, your structure should include 2 repeat units. I think this one is quite, I think took time to draw. Okay, but the important thing is you need to be certain what is happening over here. So you need to be certain Cl and one of the H, okay, will join together. And one of the H will join together with the Cl, and then you have Cl. So it means that if I can join this and then show 4 repeating units, okay, I can 2 repeating units, sorry, 2 repeating units. I can tell, okay, this is the polymer and I get the mark. So you can see this is 1 repeating unit, another repeating unit. So how to do? You see the Cl, okay, already reacted, okay, and then you have this Cl gone, H gone, so A plus HCl. Okay, so here the C double bond O, it is going to join with the nitrogen containing the hydrogen. So you will get something like that. Okay, you just join them together and you will get this polymer. Okay, this polymer, they didn't tell, okay, how much moles of water that you HCl that you are going to have over there and so on. They don't want you to learn about that. Okay, but okay, that's going to be the structure. Now place 1 tick in the table. Okay, this one read properly. Even I was doing it very fast. Okay, I also thought that they are asking for all, so I was ending up answering for all. Okay, it means I was answering polyalkene, is it addition or condensation? So I say, okay, polyalkene is addition, polyamide condensation, polyester condensation. I end up ticking 3. Okay, but I didn't read the question properly. You need to read the question properly. They are asking that whether this reaction, 1 tick in this reaction to describe polymer P. So when I look at polymer P, so it's you are going to get this molecule. Okay, you are going to get this. Okay, which is going to be what we call as peptide linkage. Okay, or amide linkage. So in this case, this is going to be amide structure. If it is amide structure, we call it as polyamide. Okay, so here this should be polyamide, and the type of polymerization is going to be condensation. Addition is going to be whenever we have carbon-carbon double bond, then we have addition. So this one is a condensation reaction. Next question is this state whether the polymer P is biodegradable. And then they're asking a reason for the answer. So biodegradable means whether this polymer can be broken or not. Okay, if I look over there, the monomer, this polymer can be definitely broken. So how you break this bond? Okay, so you can do hydrolysis. Okay, hydrolysis, you can do it either with acid or you can use with the concentrated sodium hydroxide. So that bond can be broken. If it can be broken, okay, so there are 2 ways where the bonds can be broken. One is going to be through hydrolysis. Another type is going to be the photochemical reaction. It means when you have a certain amount of sunlight, okay, or UV light, okay, the bonds is going to be broken. So please read on this. Okay, but for this question, it's going to be condensation, which is related to polyamide. Now, state, okay, yeah, can be hydrolyzed. Okay, state a suitable region to produce benzene 1,4-diol, okay, chloride. It means diol chloride. It means something to do with this. From something that has benzene 1,4-dicarboxylic acid. It means something that has this. And they say dicarboxylic acid. Maybe they have something like this. So I want to produce this from there. How do you produce? Okay, from carboxylic acid to become acyl chloride. Okay, you can change carboxylic acid to acyl chloride. You can change halogenoalkane to become acyl chloride. Okay, by using three methods, and I have written down all the three methods for you. You can choose. Okay, do remember it's also applicable for alcohol. It is also applicable for halogenoalkane, and now it is also going to be applicable to our question over here, which is going to be applicable to how do you form benzene 1,4-diol chloride, okay, from benzene, okay, applicable. If you are using PCl5, okay, you can reach that. Okay, if you are using PCl3, if you are using SOCl2, okay, you can have the acyl chloride. But we do have side products. Okay, the side products is going to be, if you are using PCl5, the side products is going to be POCl3. It's going to be one of the side products, and ACl. If you are using PCl3, the side product will be H3PO3. If you are using SOCl2, the side products will be SO2 and water. So which one you choose? Choose wisely. Okay, in this case, you can choose any three. Okay, and then they say state suitable agent. Okay, suitable agent is there. If they ask you the condition, okay, please remember this. PCl5 don't have special condition. SOCl2 don't have a special condition. But do remember SOCl2, they are used to identify alcohol group. Okay, they are used to identify alcohol group. But in this case, okay, please remember one condition. PCl3, if you want to form the H3PO3, okay, PCl3 will require heat. You cannot do this, okay, without the presence of heat. Okay, so it requires heat, and the PCl5 and SOCl2, okay, you do not need heat. Okay, the number 5. Benzene 1,3-diamine can be formed, okay, from using benzene using the reaction sequence shown. Okay, this one is quite easy. Yeah? So this one is going to be, you are adding the NO2 into the benzene ring. So if you are adding NO2 into the benzene ring, okay, this is nitration. So what are the regions that we use? Okay, we use concentrated H2SO4 and then concentrated HNO3. That's going to be the region. And then if they ask you conditions, okay, if they don't ask, no need to give. This one based on our previous practice in the passé paper, 50 to 55 degrees Celsius. But in our textbook, we learn as 55. Okay. Now, step 3. Here you see nitrobenzene, okay, dinitrobenzene. And then I'm going to get this. How do I get phenylamine from nitrobenzene? Okay, this reaction, okay, must be, you are using concentrated nitric acid, okay, and you are using concentrated sulfuric acid. Sorry. Concentrated nitric acid and sulfuric acid is going to be for nitration. So this one you need to reduce. Okay, so you need to reduce. So therefore, okay, you are using SN, the tin, okay, and the HCl, concentrated HCl, and you heat them. Okay, tin and concentrated HCl heated, but they didn't mention about conditions, so no need to mention the condition, is still okay. Okay, thin and concentrated HCl. Proteins are natural polymers. Okay, a protein is said to have primary, secondary, and tertiary. You see here, one entire chapter, 3 marks only. Okay, not only 3 marks, I think they ask this and this. So total, I think you have 6 marks from one chapter, okay, that we have learned. So here, okay, they're asking you, okay, what is meant by primary structure? Okay, primary structure is going to be any structure that has this sequence of order of amino acids. Okay, so sequence of order of amino acids, okay, is going to be there. Okay, and then what is secondary structure? Secondary structure is going to be sequence of order of amino acids that can be existing in alpha helix and beta pleated. Okay, so alpha helix and beta pleated, they have mentioned this in the marking key, so you can also check again. So that is secondary structure. And then tertiary structure is going to be a little bit more advanced. What is the meaning of tertiary structure? It's going to be involving folding of the chain. Okay, you can have more branches, more folding of the chain, and it will give you some sort of a 3D shape. Okay, it will give you a 3D shape. And in order to maintain that 3D shape, you need to make sure, okay, that it means in maintain the 3D shape, it means the stabilization. Okay, the bonds are stabilized. So how do we make sure the bonds are stabilized? Because of the presence of C double bond O and NH. So these bonds, okay, not together. Okay, it's an interaction between them. Okay, this interaction between them will keep the stabilization of the secondary structure. Okay, there is wait, let me think. Stabilization of structure. Okay, I wanted to say something, but I forgot. Yeah, there is another one, okay, which is going to be the quaternary structure. Okay, do remember the quaternary structure. What is going to be the one that is going to stabilize? Okay, so do remember, if it is going to be primary, it's going to be covalent. Okay, the covalent forces of attraction. If it is going to be secondary, then we are talking also, okay, for example, maybe we are going to talk about, okay, this hydrogen bonding, okay, and so on. That is going to be for secondary. But for tertiary and also for the quaternary, the bonds that are responsible, there will be more bonds. Okay, there will be dipole. There will be ion. Okay, ionic bond. Okay, if you remember, the ionic bond can exist between ions and ions. There will be also covalent bonds. I already mentioned. Okay, so there's so many bonds. Okay, so many bonds. I think the disulfide bridges, if you can remember. Okay, there's disulfide bridges. If you have sulfur and sulfur, okay, all these bonds will be responsible, okay, to the stabilization of the structure. Okay, I will move on. Yeah. Now, butane dioic acid. Okay, do we have to mention the bonds for the tertiary in the definition? For the definition, do we need to mention the bonds? No need, because they say define only. So define, it's a folding of chain to make 3D shape. So how they are being folded, how they are going to form the bond is not important. Even here, okay, alpha helix and beta pleated also, you do not need to mention why it is going to be in helical form, why it's going to be in pleated form. No need. Okay, no need to do that. Here, name the forces I already mentioned to you. It's a hydrogen bonding. It's a bonding between CO from one molecule to another NH to another molecule. So we are talking about generally this H with O. Okay, it's the bonding between H and O. So they are going to give you the hydrogen bonding. Okay, next. Okay, number 8. Okay, it's already 12:30. Just give me a moment, yeah, so I can finish. Okay, butane dioic acid can be used, okay, to make a 3-step synthesis using ethane as as the starting material. So you use ethane. So when you get this, okay, this one there is only a single bond saturated, and then you are going to get this. This one definitely free radical substitution. Okay, free radical substitution. And then suddenly, out of sudden, there is going to be increase in two number of carbons. Why suddenly there is an increase in two carbons? The only way that you can achieve this is by adding the carbon through this this equation, where you add the KCN in ethanol. Okay, that's the only way that you can do this. Okay, KCN with ethanol. So describe the regions and condition needed for step number 1. Okay, step number 1, the region that you need to use, okay, is going to be, you are going to use Br2 aqueous. Okay, Br2 aqueous, and condition in presence of UV light. Okay, UV light or sunlight. Okay, UV light or sunlight. Name the other product also formed in step 1, which is an isomer of A. So they are telling isomer of A, so Br, so just use the structural isomer. Okay, the Br, just put the Br over here. That is also possible. So CCBr, Br. Okay, what do we call this? So this is going to be 1,1 dibromo ethane. Okay, 1,1 dibromo ethane. Give the structural formula of B. Okay, so this molecule. Okay, so after you add the KCN, the step 2, okay, what is going to be the structure? So the Br, okay, is going to be substituted. This is going to be nucleophilic substitution reaction. So it's going to be substituted with the CN. So if I just draw the displayed formula first, you are going to get this CN, CN. So if I want to give the structural formula, so I will write down CN, CH2, CH2, CN. Okay, that will be how you write. Okay. Or I think you can also write down, okay, CH2, CN, CH2, CN is still the same. So this one is not bracket, yes, CN. Now state the region and condition needed for step number 2. Okay, this one is the one, the KCN. You can use KCN. You can use NaCN. Okay, do not go and use this one, yeah. Don't go and use ACN. Okay, don't go and use ACN. This one maybe I can ask someone. Anita, why we cannot use ACN? When do we use ACN?
ACN because
okay. In this question, we can use KCN and NaCN, but cannot use HCN. Why? Or where do we use ACN? Because now we are using this KCN and NaCN with the halogenal alkane. Okay, halogenal alkane. So this halogenal alkane, okay, I'm going to just put the KCN, okay, or NaCN, okay, but the KCN and NaCN, okay, KCN and NaCN must be heated under reflux, okay, but must be with the presence of ethanol. Okay, why I'm not asking you to write HCN? Because HCN is used for the reaction with carbonyl compounds. You go and check your textbook. Okay, so carbonyl compounds, then only you use NaCN with HCN so that you get the electrophile of CN. Okay, this combo is only used with the nucleophilic addition reaction. Okay, this combo is only used for nucleophilic addition. So this one is KCN or NaCN. Choose one. Okay, why? Because we want all the CN. Okay, we want all the CN that we have, and then you do the reaction. Now, okay, let's go fast here. We have only 4 minutes. Okay, I want to finish by 12:40. Now, butane dioic acid cannot be oxidized by warm aqueous solution of any commonly used oxidizing agents, but ethane dioic acid can. Yeah. Now, do remember, okay, I want to teach you about this ethane dioic acid. Ethane dioic acid can be only oxidized by very strong oxidizing agent. Okay. So the only strong oxidizing agent, just acidified potassium manganate, okay, or acidified potassium dichromate. Okay, you choose one. Okay, but I want you to also learn, apart from ethane dioic acid, you can also oxidize methanoic acid. Okay, but methanoic acid is very reactive, so they can be oxidized even by any oxidizing agents. They can be oxidized by mild oxidizing agent like phthalate, toluene, also KMnO4, K2Cr2O7. So that one, any oxidizing agent, okay, will be okay. But this one, no. Yeah. State the products of the reaction. Okay, the product of this reaction, if you are using it, ethane dioic, you are going to get carbon dioxide and water. Okay, you are going to get these two. Okay, I'll move on here. Compare the relative acidity. Okay, very fast here. I'll just put it. Hexanoic acid is more acidic, okay, compared to phenol, compared to hexane 1-ol. How to relate this? Why it's more acidic? Okay, you just look at this structure. Because of the carbon double bond O, the oxygen is more electronegative. They will pull the electron. So the bond between the OH is going to be weakened. Okay, the bond is going to be weakened. Okay, the same, okay, applies to phenol. Okay, but it's not weakened that much. Okay, because the electrons, they will enter will become delocalized into the benzene ring. Okay, the electrons will become delocalized into the benzene ring. So what happens? This bond is also going to be weaker, but not as weak as this. Okay, but this one for normal alcohol is going to be, R group is an electron donating group. So when they donate the electron, this bond between O and H is going to be more stronger. So it means the bond cannot be broken easily. So please look at the marking key and then explain accordingly. Okay, this one I'll leave it to you. Okay, but this one, okay, I'll just tell you why there is a single peak. Okay, a single peak can happen because, okay, the hydrogen environment, the next carbon beside that don't have any hydrogen, then only you'll get single peak. Okay, so you see, most likely it's this carbon, this hydrogen, because this carbon don't have hydrogen over there. So that will give rise to single peak, or this hydrogen also here, single peak. Why there is 4 peak? Must be adjacent to it, must have 3 hydrogen. So must be this hydrogen. Why? The carbon adjacent to this must have 3 hydrogen. So you can see, you can see it's related to, okay, if the carbon, okay, related, you must have 4, must have 4. Okay, so you have this. This one, okay, Y is 2, okay, because the carbon next to it is only 1. So N plus 1, you have 2. So you just identify accordingly. Okay, it's done. Okay, next is going to be name the splitting pattern 3.3. Okay, this is going to be 4. So it's called quartet. Okay, why? Carbon next, or we don't use the next, we just say adjacent carbon. Okay, it's bonded to 3 hydrogen. Quite simple as that. Okay, and then here state the number of peak. Okay, why different number of peaks? So I wrote the, okay, the structure. Okay, it means the display formula, and then I tried to find out how many different hydrogen environment. Okay, so I know this hydrogen environment is the same as this hydrogen environment, and I know that this hydrogen environment is the same as the remaining hydrogen environment. So there are 2 environments, so 2 peak. Okay, when I have this one, okay, this hydrogen environment is the same as this hydrogen environment. Okay, and then I will also see that, okay, this hydrogen environment, okay, is different. Okay, it's different, and this hydrogen environment is different. So how many total hydrogen environment that I have? Okay, total is going to be 3 environment, which is going to lead to 3 peaks. So here when they say butane dioic acid, so 2 peak, and this is going to be 3 peak. Okay, so that's it guys, okay, for today. Okay, we will continue with the question number 9 next week. Okay, now, so here we have the structure of nicotinamide. Okay, nicotinamide. So it's going to be an amide. Okay, it's an amide. So here, okay, the nitrogen atom in the 6-membered ring, okay, has 1 electron in unhybridized p orbital. It means that, do remember they already mentioned that the nitrogen atom has 1 electron in the ring. Okay, and then this electron becomes delocalized, become part of the single delocalized system in these electrons. The delocalized system also includes the electrons from the carbon atoms, but do take note, okay, in the past, okay, when we talk about benzene, okay, benzene has 6 electrons inside. Okay, so it depends on how many, what is connected to that benzene. Yeah, so here, do take note, okay, you are not going to have 6 electrons because you are only having 5 carbon there. Okay, the nitrogen is attached directly, okay, to the system, so it's not benzene. Okay, it's not benzene over here. So here, okay, each carbon have 1 electron. So 5 electron each nitrogen. Okay, this nitrogen has 1 electron, 5 plus 1. And also they say that the delocalized electron system also includes, okay, this one we already included. We have already included the nitrogen. Okay, and then the 2 electrons from the pi bond, okay, of the carbon double bond O. It means that this electron from carbon double bond O will also give another 2, so plus 2. And 2 electrons in the lone pair of nitrogen atom in the amide group. So it means the 2 electrons in the amide also, okay, they will also go into the ring. So you have another 2. So in total, if they ask you the number of delocalized electron in one nicotinamide molecule, that is going to be 6 plus 2 plus 2 over there, which is going to be 10 electrons. I hope you understand this. Okay, 10 electrons. If they are asking for benzene alone, yeah, just benzene alone, 6 electrons. But this one is not benzene, it's going to be a different molecule. But important is to take note at the number of carbon. Okay, you have only 5 carbon. Don't include another carbon thinking that this is benzene, so you are going to have 11. No, it's not going to be like that. Now, predict the bond angle. Now, this one also very interesting question. Predict the bond angle between the nitrogen, hydrogen, hydrogen bond angle in the NH2 group in here. So it means here, okay, when we have this, normally we think that nitrogen, okay, if I draw, it's going to be hydrogen, hydrogen, then bonded with something else. Okay, we always think that nitrogen also have lone pair of electron. We always think in that way. Okay, do remember in the past, okay, we always predict our bond angle using the lone pair because nitrogen is going to be group 15. So they have 1 lone pair, okay, over there. So when in normal situations, okay, in normal situation, we always say the bond angle is influenced by the lone pair. Okay, we always count like, okay, if they ask what is going to be normal cases, okay, in normal cases, let's say I have this kind of situation. Maybe I'll just put ammonia, for example. Okay, in normal cases, okay, 3 bonding pair and 1 lone pair. What happens? You are going to have a pyramidal shape. Okay, the pyramidal shape. Okay, you are going to have the bond angle of. Okay, do remember this also. Tetrahedral is 109.5. Okay, and then if it is going to be the pyramidal is 107. Then after that, remember the bent, okay, or water molecules, they have 104.5. Okay, so now we are talking about pyramidal. We are looking into 107 degrees. Okay, but do take note. Okay, this is not ammonia. Okay, this is going to be, even though they have lone pair of electron, they have already mentioned that this lone pair is entering the delocalized system. Okay, so when they enter the delocalized system, what happens over here? Okay, so if I erase this, what happens over here? They only have 3 bonding pair. Where are the 3 bonding pair? So the nitrogen with this, okay, this is going to be 1 bonding pair, another hydrogen, so you have 3 bonding pair. Okay, so you have 1 2 3 3 bonding pair, but the one lone pair is no longer valid. Okay, why? Because the lone pair of electron went into the system, the delocalized system. So therefore, okay, we are just looking into 3 bonding pair. Okay, the bond angle is going to be 120, exactly 120. So it's not going to be 107 anymore. Okay, please take note. Okay, we are not going to consider, okay, the lone pair. Okay, this is very, very important because in AS, we always take note about this lone pair. Okay, and then one of the common mistake of students saying that, oh, you don't consider the lone pair. Okay, then it's mistake. Okay, but now in this question, it's a very good question. They already give you this idea saying that the lone pair of the electron is going to go into the ring. Okay, they already mentioned it. So if they already mentioned that, okay, the only way that we can see over here is going to be there is no lone pair over here. Okay, there is no lone pair over there because it went into the ring. You can ask me why the lone pair don't come from this. Okay, why they don't come from the oxygen? Okay, they have 2 lone pair. Why they don't come from oxygen? Because the reason is quite simple. Oxygen is very electronegative. Okay, they will pull the electron to itself. Okay, rather than giving it to the delocalized system. Okay, so basically nitrogen will not have the lone pair to itself. Okay, so that will lead to 120 degrees. Okay, let me double check whether everyone is here. Yeah, Charlton, can you understand this? Okay, everyone switch on your video, yeah? Okay, Charlton, Ken?
Can.
Okay, let's continue, yeah? Nicotinamide, okay, can be synthesized from nicotinic acid. The synthesis involves 2 steps, okay? So there are 2 steps in this, okay? What I can see over here is going to be you have a carboxylic acid, and immediately from this carboxylic acid, you want to form amide. Okay, so how do I change carboxylic acid into amide? The first thing that you need to take note is carboxylic acid generally they are unreactive. You have to change carboxylic acid into the most reactive form. Okay, that will be the main concern, the priority. Okay, so I do have the double bond O. Okay, I do have the double bond O. I think the first thing that you need to do is to make sure the OH is replaced by the Cl. Okay, and how do you do that? There are so many ways. Okay, so many ways to do that. Okay, but I will draw the structural formula of E. So first of all, you are going to change, okay, this into something like acyl chloride. Once you get that acyl chloride, the acyl chloride, they can be changed into amide. Okay, so first of all, okay, I'm going to draw. So I'm going to have this one is Cl. Okay, I'm going to put Cl. Then after that, the step 2 we will discuss later. So here, okay, what is going to happen is give the here they say after you change, okay, after you get the E, okay, they say give give the name of formula of suitable region for step number 2. Okay, so region for step number 2. Okay, so what we are going to do, we are going to change. Okay, we are going to change this acyl chloride, okay, into amide. Okay, how do you change acyl chloride to amide? So it means I don't think so. They discuss about step number 1. So I will discuss step number 1 with you. Okay. So step number 1, what is going to happen? They if they ask you, okay, how do you change that? Okay, and what is the reason? What reason is because you want to make carboxylic acid, okay, is unreactive. Okay, you want it to be more reactive. Therefore, okay, you need to have acyl chloride. Okay, and how do you get acyl chloride? Okay, you are going to react carboxylic acid with three things. Okay, please take note. This one, you can react carboxylic acid with PCl5. You can react with PCl3, or you can react with SOCl2. And all this, okay, you need to take note. There is only one. Okay, if you are using, you are going to need to use heat. Okay, PCl3 requires heat. PCl5 and SOCl2, it happens in room temperature. Okay, it happens at room temperature. And also the things that you need to take note also is going to be PCl5. Okay, the products. Okay, they are going to give you the acyl chloride with these two products as well. POCl3, HCl. You need to know how to balance them as well. And then for PCl3, you are going to get the acid and the acyl chloride. If you are using SOCl2, then you are going to have SO2 and HCl. All this, okay, you think there are two reactants here where they are going to give you steamy white fumes, okay, which is going to be the HCl. Okay, so the one, I think if you go and read more, they say SOCl2 is going to be one of the reaction that can be used to identify alcohol. Okay, because I think not only alcohol, you see alcohol, carboxylic acid, and alcohol. Okay, and the carboxylic acid and alcohol, they do react. Okay, they do react with this SOCl2 to give you HCl. Okay, so to confirm, okay, to confirm alcohol, okay, one of the tests that we use is SOCl2. Okay, this one is in AS. Okay, where you can see the white fumes of HCl. So that is going to be a test for alcohol. Okay, but this one just extra knowledge for you. Okay, that is going to be your step number one. Okay, but now they're asking for step number two. Okay, step number two is going to be there is only one reaction. Okay, the reaction is, okay, when you are using the acyl chloride, okay, this acyl chloride must be changed into amide. Okay, the only way to change this with amide is going to be by using ammonia. Okay, you need to use ammonia, and this ammonia, okay, the condition, okay, must be this one. Since this one is going to be reactive, okay, this is very reactive. Therefore, okay, when I use ammonia, I think even though if you want to use dilute ammonia should be okay. If you're using concentrated ammonia, it's also okay, but they just want the region. Okay, but if let's say they ask you to suggest the condition, I will ask you to suggest maybe concentrated ammonia with, okay, concentrated ammonia at room temperature. Why? Because it's reactive. No need to heat them up. Okay, even dilute ammonia will do. Okay, but again, okay, if you look at the reactions, okay, the reaction with ammonia, okay, if I put this, okay, when I react with ammonia, let me rewrite again. Yeah, so maybe let me just put RC double bond OCl. When I react with ammonia, what I'm going to get, okay, you are going to get RC double bond O and then NH2 plus HCl. So you do see, okay, you do see white fumes also, steamy white fumes being released. Okay, so this is going to be very important, but do take note, not only this reaction happen when you react with ammonia. Okay, you can also use, okay, if you want just like this, then you use ammonia, but you can also have substituted amide. Okay, substituted amide is whenever, like for example, no need to have NH3, you can also react with any amine. Okay, so acyl chloride can react with any amine. Okay, it can be R1 NH2, it can be R1 R2 NH. Okay, so what will happen? You are going to get something similar to this. This is what we call substituted amide. Okay, substituted amide, okay, the way they react is going to be almost the same. Okay, in order for this reaction to happen is obviously you need one hydrogen, at least one hydrogen. So you can have R1 NH2 or R1 R2 NH. It's possible. Okay, but what I want to highlight is going to be this one, where if you are using let's say for example, if you're reacting with this, okay, with amine, and then you are using this as excess, there will be something else will be formed. If you are using excess amine, this excess amine will react with the ACl that is being formed. They are going to give you, okay, if I put it over here, okay, they are going to give you this R1NH2, they are going to give you NH3 plus and then Cl minus. So it means you're going to get salt. Okay, this is just additional knowledge. Okay, when you use you want to actually form a substituted amide, and when you are using excess amine, what will happen? Okay, what will happen? Very important. Yeah, I will give you this document, the one that I scribbled over here. Okay, so that you can take note. Okay, and you can actually do your revision over there. Okay, but I will go to the next part. Okay, nicotinamide react separately with aqueous acid and aqueous alkali. This is very easy. It's a hydrolysis reaction. Complete the reaction scheme below with the organic product. So you see, when they mention organic product, when I have this acid reflux, and then when I have the alkali, okay, when I do the hydrolysis, okay, we know that this bond is going to be broken. So you are going to get a carboxylic acid and ammonia, NH3. Okay, so I know that I will get this and this, and I know that ammonia, when you react with the ACl, okay, the ammonia will react with the ACl to give you ammonium chloride. Okay, but this is acid, so acid don't react with acid. But I do not write this. Okay, I don't include this. Why? Because they want organic. Okay, they want organic product. Okay, what is organic product? Something that has carbon, hydrogen, and something else. Yeah. So you have, okay, only this, okay, carboxylic acid, and then for this base, okay, for alkali, okay, we are going to get similar. You are going to get NH3 also. Okay, you are going to get the carboxylic acid. Okay, but the carboxylic acid will react with the sodium hydroxide. So you are going to get O minus Na plus. Okay, and then ammonia don't react with any NaOH. Okay, but I do not include this because this is not an organic compound. Next question. Okay, so this one is quite easy. Okay, quite easy. Please take note, go through this again. Okay, the bond breaking, then after that identify which one will react which one. Okay, it's very important. Identify a suitable reducing agent for this. Okay, this one, okay, when you want to reduce, okay, nicotinamide, okay, this is going to be I think this one. Okay, this one you want to change this, okay, into this. So it means you want to change amide to amine. So if you want to change amide to amine, okay, the reaction is reduction, and it must be done in LiAlH4 in dry ether. So they didn't ask for condition. Okay, so write down LiAlH4. Do you need to know the name? Okay, based on the what I see from the past paper. Okay, I think most of the time the term that they use is identify. Unless they use the term name, then you have to know the lithium tetrahydroaluminate, the full name. Okay, but most of the time, okay, they ask you to identify only. Fine. Okay, but if they ask you condition, please take note, dry ether. Okay, it must be in dry ether. Now, predict and explain the relative basicity and so on. Okay, this one I'll go very fast. Okay, you can have a look also here. You have, okay, three things. Okay, one is going to be normal NH2, and then you have this, and then phenylamine, and then you have something like this. When we talk about the basicity, it means we are going to talk about the ability of this lone pair of electron to be able to be donated to the proton. Okay, so we know that, okay, all these electrons, they are going into the ring to a certain extent. Okay, to the certain extent, but the one that less, okay, that will go less is going to be this one. Okay, why? Because it's far away. Okay, it's not that there is going to be, there is one carbon and then another carbon here, so that it's quite far away. Okay, but here, okay, this is directly connected to this carbon, so of course they will enter the ring. And this one is more worse. Why? Okay, the delocalized electron, despite even though they are far, okay, but again the electrons are going to be attracted towards the O. Okay, so it's more electronegative. So which one will be gone more? Okay, it means don't attach at all to the nitrogen. To be exact, this one. Okay, this is going to be the least basic. Okay, why? Okay, the delocalized electron takes place more effectively. Okay, effectively. So this one more effectively, this one still okay, this one not so much because of the distance. Okay, therefore, okay, you just talk about the delocalized electron, have a look at the marking key. Okay, but this one is going to be most basic, followed by this one. Okay, and then the last is going to be this one. Okay, but okay, I still want to discuss about this. Okay, so the summary for today, yeah, little bit of summary. So how to make amine? Okay, how to make amine and how to make amide. How to make amine? Okay, there are 4 methods. Okay, to make amine. Okay, the first 3 methods are going to be the normal situation when you have straight chain. So you can have halogenoalkane. Okay, you can react with excess hot ethanolic ammonia. Okay, excess hot ethanolic ammonia. Do remember that this is amine. Okay, so you need halogenoalkane. And this hot ethanolic ammonia must be excess. Please take note, must be excess, because if it is not excess, the amine itself, they will react, okay, as the electrophile. Okay, they will react and then they will form some other mixture of products. Okay, please take go and see my notes on this. Yeah, and then apart from that, if you want to increase the number of carbon, then you use the KCN in ethanol and then you reflux. Okay. After you do that, you are going to get a nitrile. Okay, once you get the nitrile, you reduce them. There are 3 methods of reducing: LiAlH4 in dry ether, H2 with nickel catalyst, or sodium with ethanol. Okay, these are going to be another method. But this method we use if you want to increase the number of carbon. Then after that, you want to change, okay, to amine. Okay, and then another method is you have amide. You can reduce to amine, which is like the same case over here, by using LiAlH4 in dry ether. Do not use the NABH4. Okay, don't use that. Okay, you must have a strong reducing agent. Okay, and then the last one, I think the number 4 is going to be whenever it involves the phenyl, like for example, nitrobenzene. Okay, if you have a nitrobenzene, I write over here. Okay, if you have nitrobenzene and you want to change it into phenylamine, okay, you can do that, okay, by using the tin, okay, tin SN and concentrated HCl, and then you will get the you can get the amine. Okay, so this is going to be the 4 methods. But how to make amide? Okay, so this is what we learned today. Yeah, so you can make amide, okay, by having acyl chloride. Okay, you can change the acyl chloride, and after that, okay, you react with what? Can you react with maybe, okay, you react with NH3. Okay, you can react with NH3, or you can also react with RNH2 or R1R2 NH. You can have, okay, the amide, and this amide, whatever amide that you want, is it a substituted amide? Is it going to be a normal amide? Okay, if you want a normal amide, just use ammonia. Okay, just use ammonia. Room temperature, okay, can be concentrated, can be dilute. It doesn't matter because acyl chloride is very, very reactive. Okay, so these are the things that you learned today. Okay, very, very important. But okay, now it's 10. Yeah, just give me 5 more minutes. Okay, the height of N peak in a mass spectrum is 80. Calculate the expected height of N plus 1. Now, if you can recall this, yeah, it's a 2 marks question. This is the part that we say that I hope you remember the 1.1% of any mass spectrum. If you have N plus 1, the 1.1% is going to be for carbon 13. Okay, and I told you to memorize the formula, where we can use the formula to find the number of carbon in an unknown compound. Okay, but now the way they use the question to apply that formula is way different. Okay, way different, but it's the same concept. Okay, but I'll teach you how you can derive to that. Okay, like for example, okay, based on my statement, 1.1% is carbon 13. It means one of the carbon is carbon 13. So it means if I put 1.1% is carbon 13, it means that how many carbon in that sample is carbon 13? One atom. Okay, one atom from that sample is carbon 13. 1 divided by, okay, the overall, okay, number of carbon in that sample. In that sample, when we are talking about this sample, how many carbon that we are talking about? Okay, so here, okay, we are talking about total of 6 carbon. You see, 1, 2, 3, 4, 5, 6. There are 6 carbon over there. So normally, okay, we use that formula to identify how many carbons, but we have that data. We have the 6 carbon over here. We just use 6 and then the abundance, okay, the abundance and the abundance, okay, the peak, okay, the expected height, okay, whatever, okay, any ratio between them. So the 1, this is what I want to find, the X. Okay, the abundance, okay, for that, the height for M peak is already 80. So you put 80. And you times by 100% because I want the percentage. Okay. So this is how you derive the formula. Okay, you derive the formula. And we just cancel the percentage. And then X, okay, divided by 6 times 80. So you get 1.1 divided by 100. Roughly, if you want to memorize the formula, up to you. Okay, but I teach you how to apply. Okay, so X, you will get 5. Okay, if you calculate, okay, you will get the X as 5.28. Okay, 5.28, what does it mean? Okay, it means if I have, okay, this is M. Okay, so this is going to be 80. This is going to be 5. Okay, so the abundance of this is going to represent, because this is M plus 1, it means this is going to represent the number of sample that has the carbon 13. Okay, carbon 13. So just apply this formula. Okay, if I try to put it together, okay, when do we use this formula? Normally in your textbook, they say that, okay, identify the number of carbon in a unknown sample. Okay, they ask like that, and then they give you all the data. M plus 1 is what, M is what. Okay, so what you do normally is the same thing. 1.1% equals to, you just put, okay, what is going to be your number of carbon 13. So it's 1. I want to find the total number of carbon in my sample. I put N, and then the abundance, okay, of the 1, okay, the small abundance. So if I have 5.28, I put 5.28. And then the N I want to find, okay, the N they found out is going to be 80. So I put 80. And then I'm going to put times 100%. You do the same thing, the same calculation, okay? And you will get N equals to 6. This is the unknown compound or something like that, the carbon. And this is going to be coming back. You can actually use this to identify how many carbon that this one has. Okay, this is what we have learned. But now, okay, they are using that formula in a very interesting way. Okay, but it's still the same. That's why they give you 2 marks. It's a thinking question. Okay, it means you need to know this 1.1. They didn't give you. You must know it's 1.1. Okay, 1.1%. Okay, that's all for today. Okay, so